Thank you very much, Etienne, and I would like to, of course, thank the organizers for setting up this very exciting program and inviting me to take part in it. So I would like to speak now on quantum simulations, and quantum simulation particularly with Rydberg atoms. It's an ongoing project that we have at Collège de France, and I would like, it's merely perspectives, but I would like to discuss these perspectives because they could trigger some interest among the theoreticians in the audience, and I think it's instructive as well. So I think I don't need a long introduction here to tell you that the quantum is a marvelously successful intellectual adventure that has lasted for nearly a century now. It gives us the way to harmonize the music of the sphere, bouncing back on this evening's conference. But very importantly, it also triggered a lot of applications. Lasers, computers, MRI are all based on direct applications of the quantum science. And I think it's a very beautiful example of a long-term societal and economic impact of fundamental research, of pure curiosity-driven fundamental research. Of course, I know you are all aware of that. I wish all politicians would be as aware of that as you are. This being said, in a very interesting virtuous circle, these applications, the lasers, the computers, have provided us with tools to explore even further the quantum world, with tools to manipulate individual, perfectly isolated quantum systems, on which we can play, so to speak, the thought experiments of the founding fathers. And I think one of the most marvelous things about quantum physics is that 1 century after its formulation, it perfectly survives the realization of the mere founding thought experiments. It just behaves as they had forecasted it should. But we can also, so we have fundamental open questions still to understand about quantum measurement, about decoherence, about superposition and locality, but there are also applications. We can think of using the quantum, taming the quantum, to go to new applications. And this new application can be, as I told you, some very fundamental questions about entanglement, measurement, state superposition. But we can also think, and this is of course the core subject in this conference, of using the weird quantum logic, the superposition logic, the yes and the no at the same time, to speak as our president, to tame information, quantum cryptography, quantum teleportation, quantum computing. You can also think of using the quantum and peculiar quantum states to improve the sensitivity of measuring devices of time, of fields, quantum clocks, quantum field sensors. This is the whole field of quantum sensing. And finally, we can think of quantum simulation. How could we use a perfectly controlled quantum system, totally under experimental supervision, so as to understand better what's going on in a more interesting, more applicable quantum system. You have recognized, of course, the big pillars of the quantum initiative flagship in Europe. It's by no chance, of course. But I would like to focus on quantum simulation. And in fact, the first doing quantum simulation was Richard Feynman. You should always quote Feynman at the start of a talk, be it only for his extraordinary vocabulary. Nature is not classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, very beautiful, it's a wonderful problem because it doesn't look so easy. Real theoretical sentence, theoretician sentence. Of course, the problem he was referring to is the difficulty of many-body physics. I will just speak of many-body physics in terms of spin arrays, just to make it simple. If you want to completely calculate the evolution of an n-spin array, you are faced with the Hilbert space dimensional problem. The dimension of the Hilbert space is 2 to the n. And as soon as n is larger than 42, well, about 40, but 42 is a proper number for that. As soon as n is larger than 42, you cannot explicitly compute the evolution of the system, integrating Schrödinger equation, even with modern supercomputers. And so this is a very vivid problem. Of course, we have theoretical methods, not so often, and we have also approximate numerical methods that are highly successful. DMRG, TDMRG, MPS, don't ask me what those acronyms mean, by the way. All these things allow us to answer some specific questions on many-body systems. For instance, computing the ground state of a few hundreds of spins is feasible with a moderate computational effort, whatever the interactions can be. But of course, the questions these approximations can answer, the frame of applicability of these methods is limited. For instance, if you take a quantum system and you make a brutal quench by totally changing all the operating parameters of the Hamiltonian, the further evolution spans the whole Rydberg space, and there is no method that can make it any simpler. Not really. So the idea of quantum simulation, let's follow Feynman precepts and let's realize a system of spins, of qubits, that emulates the dynamics of a system of interest. But a system in which you can tune all the parameters, a system in which you can measure all the spins observables at the end of the evolution, so as to be able to reveal what is really important in the dynamics of a system. And as soon as you have, say, more than 42 spins in your system, it would be more efficient than classical computation. There are mainly two trends, two approaches to quantum simulation nowadays, the digital and the analog. This is very rough, of course. The digital quantum simulation is basically build a general full-fledged quantum computer and ask him, through trotterization operations or something like that, to emulate the dynamics of a system of interest. This is, of course, possible. It has been done, in particular, with ion traps in Rainer Blatt's group and in others. You can compute molecular potentials. You can do some things like that. But, of course, it's as difficult to build this system as to build a general, full-fledged quantum computer. So it's rather difficult. The analog simulation is kind of less powerful, less flexible, but certainly more easy to obtain. And the idea is don't build a general full-fledged computer, just build an n-spin system array that has exactly the same Hamiltonian as your system of interest. And build it with systems which obey some requirements that, well, basically the standard requirements of quantum computing, high-quality individual quantum system, scalable methods for arrangements of this quantum system, readout, possibility to introduce disorder to study such phenomenon as many-body localization, but mainly build the system so that the interaction between the individual components of your system can be tailored. If you cannot change the Hamiltonian, you will emulate one system. If you can tune the Hamiltonian at will, you can emulate a variety of systems. And so it doesn't look so easy, says Feynman. It's true, it doesn't look so easy, but it looks more easy than building a full-fledged quantum computer just because you need only 42 bits or so. And since it's easy and since it's interesting, well, easy with many quotes, it's a very active field worldwide. And there are a wide variety of quantum simulation experiments that have been realized nowadays. With cold atoms on lattices, with superconducting circuits, with trapped ions, for instance here in 2D in a beautiful paper by Bergquist, or on Rydberg atoms held in traps. So there are beautiful experiments going on, and I would like to show now why Rydberg atoms are particularly interesting in the context of quantum simulation. What is a Rydberg atom? Well, just an alkali atom. There are no good atoms besides the alkalis. An alkali atom in which the valence electron is promoted to very high-lying excited state with a principal quantum number n, say of the order of 50, to give an order of magnitude. And these atoms are blessed with very remarkable property. In spite of being very close to the ionization limit, they have a rather long lifetime. The Rydberg levels you can excite directly with lasers from the ground state, which have a low angular momentum, of course, have a lifetime of the order of 100 microseconds. The circular Rydberg state, which is this beautiful implementation of Bohr's classical orbit, is just an electron localized as close as possible, due to the Heisenberg uncertainty, to the Bohr orbit. Those circular states reach, for n equals 50 also, a lifetime of 30 milliseconds. The size of this atom is enormous. It's about a quarter of a micron across. They have a rich level structure. I won't go into that, but they have in one hydrogenic manifold, n equals 50, There are 2,500 levels, and you can play quantum games in that pretty large Hilbert space. And also, due to the large size of the orbit, these atoms are highly coupled to the microwave fields. They have been our workhorses for the last 40 years exploring cavity QED experiments. It was days before circuit QED. Yes, there is in history before circuit QED, but it's long past. And they are also very sensitive to external fields, electric or magnetic field. And finally, because they are large, they undergo an enormous dipole-dipole interaction. And this is, of course, the key to quantum simulation. You want fast, large interactions to simulate what is going on. Just to give you an order of magnitude estimate and recall some early experiments on that, let's imagine two Rydberg atoms of rubidium, for instance, but it has, of course, it could be any alkali, separated by a distance r, and promoted to the 60s state. They undergo a vast van der Waals interaction whose early evidence had been given in this paper long time ago. This interaction is a van der Waals interaction. It's a repulsive interaction, because those are excited states, which ranges like 1 over r to the 6. And the order of magnitude is striking. At a 5 micrometer distance, these two atoms have an interaction energy of nearly 10 megahertz, which is, of course, very fast, meaning that sort of a logic gate between those atoms could be driven in a time of 10 nanoseconds. So it's very large, and it's very large also as compared to the typical kinetic energies that you can find in the cold atom clouds. More on that in a second. So that fierce dipole-dipole interaction has some very interesting manifestations that have been explored since 2001 basically under the impulsion of a seminal paper of Misha Lukin on dipole blockade. So the basic idea of dipole blockade is pretty simple. You just consider two atoms, both in the ground state, one in the Rydberg, two in the Rydberg. Obviously, they are both in the ground state. They don't interact at micron distance. Standard van der Waals would be kilohertz. One ground state and one Rydberg barely interact, but two Rydbergs strongly interact. It means that if you shine on this pair of atoms a laser that is resonant to excite the first Rydberg atom, it can excite the second if the distance is large. Obviously, if they are separated by the size of the universe, it should be okay. But if they come close together, the van der Waals interaction shifts the line to excite the second Rydberg atom out of resonance with the transition to excite the first. And you can excite only one atom. And this, of course, leads to mechanisms that can be put in terms of quantum gates. If you consider a dense sample of ground state atoms, imagine that this one, the green one, is excited into Rydberg. Immediately, it precludes excitation of all the other ones within a sphere whose radius is called the blockade radius, and it's just determined by the fact that the blockade radius is equal to the line width of a transition, the van der Waals interaction at the blockade radius is equal to the line width of a laser excitation, be it a technical or a fundamental line width. So you imagine that in such a sample, you cannot excite many atoms, and they would be very far apart from each other. There is a different regime that is called the facilitation regime. In that case, you tune the laser out of resonance with a one photon line, with the one excitation line, but you tune it to the blue. So that the excitation, which is now a two photon excitation, is not resonant if the atoms are far apart, is not resonant if the atoms are very close by, but is resonant for a specific distance between the atoms, called the facilitation radius. It means when you excite the first atom, the next one will be excited about at the facilitation radius away. And the next one in a shell determined by the first two shifts, and so on and so forth, and you would create some sort of order and bunches inside the medium. So this is interesting. I would like just to say that we have started experiments. I will mainly speak of perspective some time ago about that, and we have performed some experiments on Rydberg excitation on a cold atom cloud. Well, you want atoms at a few micron distance, so you need a pretty high density to start with. And to get a pretty high density, the best is to go to a superconducting chip, to an atom chip, sorry. And since for Rydberg atoms' sake, it's good to be at low temperature, they are very sensitive to blackbody fields, we have used a superconducting atom chip. So we have designed an experiment, we prepare a sample of ground state atom close to BEC condensation, and we shine a couple of lasers that drive them on a two-photon transition from the fundamental to the Rydberg states. All that is very standard. We can excite the atoms and we can detect them with feed ionization. An interesting thing about Rydberg atoms is that you have a powerful investigation tool that is microwave spectroscopy. Instead of just looking at the laser excitation line, you can perform microwave transition and field ionization distinguishing various ends in the Stark manifolds. You can think of making spectroscopy of the Rydberg atoms. And for instance, in this case, if we excite all atoms in the 60s state, there is an interesting property of the interaction. If you look at this atom, the frequency, its frequency, the transition frequency from 60s to 57s in the presence of all the other atoms is shifted by the van der Waals interaction. And the amount of this shift is precisely proportional, with a 1.3 factor, to the initial van der Waals energy that the atom had in the cloud of 60s atoms. It means that if you record a microwave spectrum of your sample, you get directly a spectrum of the van der Waals interactions within the spectrum, within the sample, so you just get information about the spatial arrangement on the atoms in the sample. Indirect, not an imaging, but some direct information. And here are the spectra that we recorded in 3 different situations. So it's a microwave spectrum, and we just scale it with a scaling factor in terms of the average interaction energy in megahertz. When I tune the excitation laser at resonance, I'm in the dipole blockade regime. I expect that all atoms should be excited at a large distance with respect to each other. I thus expect that the van der Waals average energy should be weak of the order of the laser excitation line width, a bit less than a megahertz in our case. And this is what we observe. We observe a line that is barely shifted with respect to the isolated atom line, and whose width is of the order of the laser line width. We don't image that directly, but we can compare to simulations. So we have put forth a Monte Carlo simulation of the excitation process. Well, it's not full quantum, but it contains some quantum features. In yellow here, the dots represent the ground state atoms in the sample, a few thousands of ground state atoms. And the big circles represent the radius of the Rydberg atoms, the blockade radius, of course, not the actual radius. And what you see is the following. You have some atoms, but they are very far apart, typically 1 exclusion radius apart. And in fact, the cloud of Rydberg atoms is much larger than the cloud of initial cold atoms. Why is it that? It's not a BEC, the density doesn't drop exactly to 0. It's a thermal cloud. And because of a blockade, it's better to go far in the wings of a thermal cloud to excite atoms far away from the others than trying to excite more atoms in the bulk. So you get a very large atom cloud. The situation is very different if you tune the laser out of resonance, the excitation laser, by 1 megahertz or 2 megahertz. In that case, you enter the facilitation regime. To compensate for the laser detuning, you must excite atoms that are at a small distance with respect to each other, and hence you expect the average van der Waals energy to be larger, and larger by an amount that is of the order of the laser detuning. Well, there are factors, but of the order of the laser detuning, and it's what we observe. And the numerical simulation confirms that we have less atoms because we are off resonance for the excitation, but these atoms are densely packed and even more densely packed than the initial cloud. So it's a very clear manifestation of a dipole blockade and of a facilitation regime. What is important there, and something you should not overlook if you are planning to do Rydberg atoms experiments, is that you can look also at the dynamics of the atom. what we do is that we excite the atoms in that configuration. They have a pretty large average energy of the order of 2 megahertz. And we just record the microwave spectrum as a function of time from laser excitation. At very short times, we observe the wide line that we had before. It's scaled down so that we can see. And you see that as time goes, the line narrows and gets back to the position of unperturbed atom. Why is it? It's not because we lose atoms. We lose some in this 100 microseconds, but not enough to justify this dramatic reduction of the line. It's just that we are in a cloud at 1 microkelvin with typical interaction with typical kinetic energies of tens of kilohertz. And we suddenly give to these atoms a potential van der Waals energy of the order of 2 megahertz. They just fly apart. The cloud of atoms just explodes, and very rapidly so. The size is multiplied by a factor of 2 in a few tenths of microseconds. So it says something. It's very good to have Rydberg atoms because they have a very, very large interaction. But you can't use very long because they have such a large interaction that they fly apart in no time. And this is a very strong limitation to the so-called frozen gas approximation that is often made in these circumstances, which is certainly valid for short time intervals, but certainly totally invalid for long time interval or long excitation pulses. Okay, so these are, of course, not very exciting experiments. There are more exciting experiments going on with quantum simulation on Rydberg atoms, particularly in the groups of Immanuel Bloch with optical lattices, excited or dressed with Rydberg atom character, and they have observed beautiful crystalline structure due to the dipole blockade in those samples with an atomic microscope. Experiments on the excitation of a chain of atoms to the Rydberg states in the group of Misha Lukin. They have performed a beautiful experiment on the chain of 51 atoms that they excite in the Rydberg state. And what you see is that after some time, you excite one atom over 2, which is a manifestation, an evident manifestation of a dipole blockade regime. And they have other regimes in which you have 1 out of 3, 1 out of 4, and they have quantum phase transitions between that. And a beautiful experiment also is performed in Orsay, in the group of Antoine Brouwes. They can make a perfect arrangement of ground state atoms, 7 by 7 by 7. They excite to the Rydberg states, and they record also some antiferromagnetic correlations in the system. So these are beautiful illustrations that Rydberg atoms can indeed be used for experimenting on quantum simulation, but yet these experiments face limitations. Well, we have to face another limitation, which is that our experiment is not operating yet. But they have to face limitations, which are basically due to the finite lifetime of the Rydberg atoms. They live 100 microseconds. It's long, but it's not very, very, very long if you want to study long-term dynamics, such as those occurring, for instance, in medi-body localization, in glassy dynamics. You need to look over long time scales for your quantum simulation. And this is certainly a problem. And it's even more a problem because all these experiments are performed at room temperature. Rydberg atoms are very sensitive to blackbody field. And as shown by Trey Porto some time ago, those blackbody field induced transfers considerably modify the dynamics of the Rydberg atom cloud. So this is one problem. Another problem, which I just evoked and showed experimentally, is atomic motion. In all those experiments so far, you start with an optical lattice or a set of optical tweezers. So the ground state atoms are indeed very well trapped, but the Rydbergs aren't. So they will fly away, also limiting and very severely the typical interaction time that you can access. So that is so to some extent reduced but not totally cancelled by just dressing a round state with an unresonant laser with a bit of Rydberg character. But basically what you lose on the interaction, you also lose, what you gain on the lifetime, you lose on the interaction, so it's not clear. So the question is it possible to operate with long-lived Rydberg atoms trapped themselves in an optical lattice and to build a quantum simulator based on Rydberg atoms and particularly on circular Rydberg atoms. So in the next 20 minutes or so, I would like to discuss this proposal that was recently published. So why the circular Rydberg atoms? First, because we have worked with them for 25 years, so we know them a little bit. Second, because they have, even in the field of Rydberg atoms, they have some very remarkable properties. And the first is the lifetime. The n equal 50 circular Rydberg atoms lives for 30 milliseconds. 48 lives for 25 milliseconds. So it's already a pretty large lifetime if you put it on the scale of a Rydberg-Rydberg interaction, which once again is in the, between 10 kilohertz and megahertz range. So it's pretty long. But it's not long enough. French people tend to be ambitious and arrogant, so we want even more than that. And to get even more than that, we can remember Dan Kleppner-Sepinal papers on 81 and 85, sometime before many people in this audience were born. This paper showed that you can enhance considerably the lifetime of circular Rydberg atoms. In fact, at 0 temperature, spontaneous emission can take place only on the 1 microwave transition between the circular state and the immediately lower circular state, just due to selection rules. This transition is sigma plus polarized with respect to the axis perpendicular to the orbit of the electron. So the precept is very simple. Just put this atom inside a capacitor, two-plane parallel sheet of metal. This capacitor provides an electric field which is anywhere required to stabilize this very flat and anisotropic orbit of the circular atom, and just make that the spacing of the plates is lower than half of the radiated wavelength. If this is the case, for this polarization, you are in a waveguide below cutoff. There is no mode the atom is coupled to. And so the atom just cannot radiate. So it's very simple, and Kleppner demonstrated already in 85 together with Randy Hewlett an improvement by at least a factor of 20. It was most probably much higher. So we have made numerical simulations of that. You just take versus the distance between the plates and the size, lateral size of the plates. You take golden plates, you cool them to 0.4 K, because of course you inhibit spontaneous emission, but you have pi polarized transition to upper manifolds which are not inhibited, so you have to be cold. But 0.4 K is just mild temperature as a matter of cryogenics. And you compute the lifetime enhancement or the spontaneous emission rate reduction, and you get extremely large figures. So it's a numerical computation of a radiation of a dipole between two plates. So there is no theory there. It takes into account everything. And you see, for instance, that here with a 2 millimeter by 13 millimeter capacitor, we could reach a lifetime for an individual atom of nearly 1 hour. This is, of course, very ambitious, but it's promising. Of course, if you want to keep an atom for 1 hour inside a 2 millimeter condenser, it's easy to show that you have to trap it, unless it falls. And space station is not an option. They don't admit scientists above 60. So it's not an option. So we need to trap the atoms. And there also we can rely on a proposal by Ben Varco in 2000. He said that circular Rydberg atoms can be laser trapped. Why is it that? Because fundamentally a circular Rydberg atom is one free electron and far away vaguely bind an ionic core. And that one free electron placed in a laser field undergoes a ponderomotive energy shift, that is a master degree exercise or even undergrad degree exercise to compute, which expels the electron out of the high field regions. The electron is a low field seeker, and hence the whole Rydberg atom is a low field seeker. So you can trap it in a minimum, local minimum of a laser intensity. Like a blue trap, if you wish, for those fond of atomic traps. Just because the electron being free, any laser is blue with respect to its resonance. And it's a rather large trap. The polarizability is about that of a rubidium atom if you use a 1 micrometer wavelength laser. So it's a rather deep trap. It's also independent of the principal quantum number because basically you trap the free electron. So it means that two Rydberg levels see basically the same trap potential. And basically, you don't see any trap-induced decoherence. It's a kind of everlasting magical wavelength arrangement in which the trap is independent of the frequency. Of course, you all think this guy is crazy. What about photoionization? And it has been proposed to trap Rydberg atoms. There are beautiful papers by Max Safman on that. And he made even attempts and calculations. And if you take a low L laser accessible SPD or F Rydberg atom and put it in a typical trap laser, it ionizes in a time of tenths of nanosecond. So it's dead. But it's not the case for circular atoms. Why is it that? To photoionize, basically, you need to start with an electron which has, in a very crude qualitative picture, which has the same final momentum as when it's expelled out of the atom with a typical photon energy. Since the photon energy is of the order of one optical wavelength, it means that the electron should be in a radius from the core of the order of a Bohr radius, or a few Bohr radius. Of course, for low L atoms, they often go in Seves region and can be photoionized. But the circular atom has an exponentially vanishing probability of presence on the core. And it will never photoionize. So, of course, never trust qualitative arguments. You can go to the hydrogen atom. Quantum defects are 0. You work out the hydrogenic photoionization formula. It's a bit large, but it's feasible to track it. You make the numerical application. And in a 1 watt, 10 micrometer square laser beam, you get a photoionization lifetime of 10 to the 175 seconds, which is sizably larger than 10 to the 30 times the age of the universe. So I think we are safe, even if I made a pi factor in my calculation, which could happen, I have to admit that. So they are impervious to photoionization. Very good. So the kind of trap we are envisioning is this. Just a plain parallel capacitor. We have 2 millimeters across, so we have plenty of space. A Lagergos beam, which provides a radial confinement of the atom. And then we need a lattice with a spacing of the order of a few micrometers, preferably an adjustable lattice. So we'll just go for 2 1 micrometer laser beams, intersecting at a small angle. And by changing the angle, you can easily change. Well, all that is theoretically easily, because you have a bit of optomechanics in there, changing the spacing of the lattice. And you see here the trap. It's a pretty deep trap. It can be made isotropic with similar oscillation frequencies. The typical oscillation frequencies with 1 watt lasers, more or less, is of the order of a few tens of kilohertz. So that's okay. It's a pretty deep trap. It works. Of course, when I spoke of the lifetime, that was the ideal lifetime for an atom that is only subjected to residual spontaneous emission and blackbody-induced transfers. You have to bookkeep all other sources of losses. So some are negligible, like photoionization or dipolar relaxation, atom exchanging states. Some are more annoying, like collisions with background gas, made an estimate of 400 nanoseconds. The good news about cryogenics is that 0.4 K, provided you don't have an helium-free leak, everything is condensed. Nothing moves. Vert has measured at 4K a vacuum lower than 10 to the minus 17 torrs. So it should be feasible to reach pretty good vacuum. And we have done that already. You have a Compton diffusion by the trapped electron that can contribute. This is an effect which is not very easy to calculate, but the rate is low. It's 200 seconds. The main rate of loss is, in fact, the van der Waals interaction itself. Quantum mechanically, if the atom goes close by, you have an interaction because you mix levels. And you can mix the circular states with levels whose spontaneous emission is not inhibited. Classically, when the atom comes close by, the orbits tend to tilt, and they have a little of coupling to the pi polarization, which is not inhibited. But that you can compute, and you find at the end of the day a total lifetime of the atom of 50 seconds. Meaning that a 42, should be 42 atom chain, can live for over a second. So this is the order of magnitude we have to remember. Now, how do these atoms interact? Now we have a choice to make. We want to implement spin 1/2, so we want a two-level situation, but we have to choose the level. So first one is easy to choose. We choose 50 just because it's 50. Well, Brossel, you see, it's a kind of compromise between the highest possible n to get a long lifetime and a large interaction, and the sensitivity to stray electric fields, which, of course, also increases enormously with n. So let's say the first is 50. So a natural choice, of course, would be to say, I take a spin system in which I take the circular state 50 as the up state, and the circular state 49 as the down state of my spin. Well, in that case, it's okay, but you have the van der Waals interaction 50-50 and the van der Waals interaction 49-49, both repulsive, which range like 1 over d to the 6, and which are moderately large. But you also have the exchange interaction, 49-50 goes to 50-49 by exchange of a virtual photon. This exchange interaction is resonant. This exchange interaction is at the first order in the dipole-dipole coupling 1 over d cube. So this exchange interaction ranges like 1 over r cube, and it's very, very, very strong. It's the one that is used in Lukin or in Brouwer's experiments, basically. It's very, very strong. And being very strong, it can be too strong for the trap, which is not good news. And also, one of the requirements that we have for a quantum simulator is being able to tune the Hamiltonian. And to tune the Hamiltonian, it should be good to balance between the direct 49-50-50 and the exchange interactions. And there we cannot, because the exchange just overwhelms all the others. So it's not a very good choice. Well, we'll try it, of course, but it's not the best choice. The best choice seems to be to encode the spin of the 50 and 48 level. Why is it that? Because then the exchange interaction is a virtual two-photon transition between the two atoms. It acts at the second order in the van der Waals interaction potential. And hence it's also like 1 over d to the 6. And it's in size comparable to the direct interaction. So it's why we want to code on that. Of course, if you just do that, the ground state is simple. All atoms in 48. Just because there are nearly 160 gigahertz between the two levels. So whatever the interactions, ground state is trivial. So if you want a bit more fun, as the untrapped people do, you have to dress the atom with a microwave, nearly resonant, that admixes the two levels, and that, so to speak, cancels the atomic energy. So we just shine a two-photon transition with a Rabi pulsation omega and a detuning delta, and we turn the crank of interaction representation and a little bit of error, and we find this Hamiltonian. So sorry, it will be the only complex formula there. But what do we have in that? So the sigmas are, of course, relative to the atoms. This is for a chain of atoms, indexed by J. We have here a sigma z term, which is represents a common magnetic field in the z direction. And it's proportional to the source detuning. We have the omega term in the x direction that is proportional to the source power. So both of that are under complete control. We have a ZZ interaction terms, which originates from the van der Waals interaction 50-50 and 48-48, with a coefficient GZ, and a G term, which is nothing but the spin flip-flop between two adjacent sides. What can we say of this Hamiltonian? It's an XXZ Hamiltonian in transverse field. It's kind of a workhorse of spin chain physics, and it's quite a general, as we will see, Hamiltonian. The J parameter here is fixed. It depends only upon the distance of the atom. We'll dress the atom with an electric field. We have seen that. We'll also use a magnetic field, just in order to reduce a little bit the lifetime reduction due to the interaction. A little bit of magnetic field removes unwanted degeneracy, and it helps. But J is basically fixed. It's 17 kilohertz at 5 micrometer, 2.3 kilohertz at 7 micrometer. Of course, it's a differential shift effect, so it's less than the direct van der Waals interaction. So this sets the fundamental time in this experiment. The spin exchange time is 1 over 4J, with the definition I used there. So it's in the 10 to 100 microsecond range. And once again, the chain is supposed to live for 1 second. So between 10 to the 4 and 10 to the 5, basic interaction time. This is the good news. This is something that is very hard to reach, for instance, with cold atoms. The lifetime is long, very long, but the exchange is much lower. And the interesting point is that delta and omega can be tuned, but Jz also can be tuned. And this is a beautiful plot of Jz over G for various magnetic fields and various electric fields. And what you see is basically that Jz over J can be tuned all the way between -3 and +3. Of course, you have to make compromises. The lifetime is integrated by this shade of yellow. The more electric field, the more magnetic field, the more the lifetime. And if you go there, you lose a little bit of the lifetime, but okay, that's okay. All that is a practical range. And why is it that? Just because this van der Waals interaction depends upon coupling of 48-48, for instance, to many pairs of levels, where you make one transition in which, one transition in the other. And all these levels have positions in the energy spectrum that depend upon the electric and the magnetic field through the Stark and Zeeman effect. So you have kind of resonances, kind of variation that explain this sharp variation of Jz over Z versus the electric field. It's good to be able to span this whole range because this is the phase diagram of your system. So it's a very rich phase diagram. It's computed here for delta equals 0, following a paper by Dimitri F. et al., as a function of omega and Jz over Z. And there are a variety of phases. There is a paramagnetic phase in the x direction, ferromagnetic phase in the z direction, two Néel phases in the x and y direction, and a variety of quantum phase transitions between them and a variety of critical points and things like that. I'm totally ignorant of many body physics, so I do speak under control. And so we could explore all of that. Could we reach the thermodynamic limit? Well, we made, together with Guillaume Roux of the LPTMS, we made a matrix product state calculation for 40 atoms. And already at 40 atoms, if you define the proper observables, basically spin correlation functions, they reproduce fairly well the expected phase diagram. So 40, we are already somewhat in the phase space diagram. So, of course, I would say all that relies on the fact that you should be able to realize a chain of spins without defects. If only one atom is lacking, due to the 1/d6 dependence, basically you have two independent chains. So we need a unit filling. That's not easy. This is easy in the Mott regime for cold atoms, but Mott regime at 5 micrometer distance is not reachable. And moreover, the excitation probability to circular state is not unity. It's 95%, but it's not unity. So we need to be able to do that, and we have proposed an interesting variant of the evaporative cooling method to do that. Just in a nutshell, you start with an elongated sample and prepare Rydberg atoms in blockade regime. So you have about 100 Rydberg atoms randomly distributed on this 1D sample. You trap in the Lagergos beam, and you install two plug beams that block both extremities of a cloud. So basically, you have 3 atoms in a 1D arrangement. It's Tongs-Girardot, it's Luttinger, it's all kind of thing, but it's truly classical, interacting between these two plugs. One plug is hard, one plug is weak. And you just make the plugs come together. So you compress the cloud of atoms. The energy of interaction increases. And at some point, the last atoms takes a positive energy fluctuation to be ejected over the barrier, and it evaporates. But since it takes a little bit of extra energy to get outside the barrier, it cools effectively the others. And we have numerically computed that, so it's not that easy because it's a highly chaotic system. And this is the number of atoms as a function of the length of a chain. So we start here, we compress, and we see that we have a nice plateau on which the atom number is entirely determined by the trap, whatever the initial conditions. Here I have something like 100 samples. And moreover, if you look at the trajectories, I have no time to, you see that the average kinetic energy is going down. So in about 1 second, which is good compared to the lifetime, we can prepare a defect-free chain of atoms. And after that, either you can trap it in the 1D lattice, or you can use tweezers to move the atom around. You have plenty of time for that, for a 2D or a 3D arrangement. So it seems encouraging. Of course, you have to take into account all possible defects. You can also use that for state detection. Just resume the evaporation, send the atom pop, 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 one by one to a detector, and record their states. So we have made also numerical simulation to check that the residual motion of the atom is not a problem. The atoms are not cooled once they are in the Rydberg state, We're thinking of it, but they are not yet not cool. And they are typically, in the lattice that we are envisioning, about 4 phonons of excitation. So we have to take that into account, and together with Guillaume, we made a remarkable tour de force calculation in which he simulated a slow quench and adiabatic evolution from the ferromagnetic to the paramagnetic phase and back, taking into account all the imperfections in the motion of the atom, treated classically. This is, of course, the first approximation. And in all that, and what he observes is that, as ideally expected, we return into the ferromagnetic initial state with a 99% fidelity. So we can cross this QPT back and forth, and we get back to the initial state. The only condition for that is to tune J to be smaller than the trap oscillation frequency. If you tune J to be the trap oscillation frequency, you get some beautiful resonant effects which have nothing to do with the initial system. So, of course, there are interesting things that we could do with a simulator. Exploring the phase diagram, you can do that with MPS. So I think nobody would be excited by that. But doing quenches, defects of adiabaticity, introducing a bit of disorder with a laser speckle field, as in all standard atomic experiments, could lead to MPS and glassy behaviors. We could think of having 2 chains of atoms coupled ferromagnetically or antiferromagnetically so as to implement Haldane dynamics. There are certainly things that we could think of doing, and we very much look forward to receiving input from our theoretical colleagues. I more or less understand what a 2-level atom is. For a chain of 2-level atoms, I have more difficulties. Okay, so I would like just to conclude by pointing out the people involved. So Michel Brune will be the leader of the group as of next January. Sébastien Glaise, Igor Donsenko, and Clément Serrin are the permanent members. Serge is also with us. And on the circular state simulator, Tanlong and Nguyen played Totigan Cantra, Rodrigo Cortinos, Brice Navon, and Paul Meignery are working on that now. And what we are trying to do is first trap a circular atom and check by spectroscopy that it behaves as it should. And we have some funding, so there are positions available in the group. If any one of you is interested into very practical experimental work, you are certainly welcome. And we'd like just to mention, passing by, that I'm also the lead editor of Physical Review X, together with Christina Marchetti. So even if you want to retribute us for throwing away one of your papers, or if you want information of this journal, I will be here to discuss it with you. Thank you for your attention.
So thank you, Jean-Michel, for a very exciting talk, and we have a few minutes for questions. Yeah.
Hi, thank you for this beautiful talk. You mentioned choosing n equals 50 as a compromise between enhancing Rydberg effects and limiting the sensitivity to stray fields. Could you comment maybe on the, I don't know, tell us a bit more on what you expect to be this effect of stray electric fields, and do you plan to actively control them?
The effect of stray field is the nightmare of everybody involved in Rydberg physics. The Stark polarizability is like n to the 7. And n to the 7 is a large factor when it comes to n equal 50. I'll let you do the application. It means that fields of a few millivolts per centimeter are able to shift appreciably the lines. It will certainly be a problem in our experiments for 2 reasons. First, we need all the atoms to sit at the same frequency within something that is much better determined than the J, than the exchange. And so we need to have a good control of electric fields. We made recently some good some good progresses with that, with our atom chip experiment. One of the keys of this experiment might be, one of the key problems is contact potential. You have gold, metal, but you also work with rubidium, and rubidium deposits on gold. And since we are at low temperature, everything sticks. So the rubidium patches everywhere, and that creates potential. So the only way is to make the experiment out of rubidium. No, to rubidium plate all of the experiment to avoid this contact potential. It seems to work. Up to which extent is something that needs to be determined. The good news here is that we are a millimeter away from the surfaces, much farther than we were in the atom chip experiment. So we hope it not to be too severe a problem. But going to 70 or 80 would be a problem, certainly. And then the good news about 50 is that the microwave frequencies is 50 gigahertz, and it's good because you can get rid of thermal effect by a moderate cooling. 0.5 K is enough. If you go to 70, you need to get to 20 milli-K. And putting 2 or 3 watts of trapping laser in a dilution fridge, I don't feel it very well.
Other question? Yeah.
You mentioned that the vibration do not make a problem for the particular simulation problem that you have in mind, but I would imagine that this leads to some kind of T2 degradation of each qubit.
It leads to even more interesting. I even made a master degree exercise out of that for my master degree course on atoms and photons. If you take just 2 atoms and include the van der Waals force and the spin exchange, you will find that due to the spin exchange, the spin state entangles with the motional state. And you get beautiful Schrödinger cats of the motional state in which the vibration of the atoms is one phase of the other depending whether you are exchanging or not. And that, if you trace out the motion, it scrambles the field exchange. Exactly. So it's a beautiful, and certainly there would be very interesting dynamics. It's very hard to get into that analytically, at least for my analytical capabilities. And it's impossible to get into that numerically, just because you had to chain a spin, a chain of coupled harmonic oscillators. And you need at least 3-4 states per. So numerically intractable after 3-4 atoms. But it's certainly an interesting problem to look at. So it's an excellent quantum simulator, but a slightly different system, which is a spin boson non-trivially coupled system. Mm-hmm. But it could be of interest, of course. And it's easy to go into that regime because what you have to do is just to adjust the trapping frequency with respect to the interaction of the spins. If you go to very shallow traps and strong spin exchange, you will be in a regime of total entanglement. So you just need to crank down the laser power and to diminish the distance. It's certainly an interesting perspective, but far out of our theoretical reach.
One last question. No? So if... oh, sorry.
Could you comment on your strategy for detecting the states of the atoms at the end because of these 2 capacitor plates?
I have been very fast on that. I apologize. So the idea is you let your chain interact. At some point, you cast the 48 atom, the 48 level on 46, with a hard 2 photon pipels that affects all atoms. And the 46 to 50 exchange interaction is 0. It's millihertz, because delta n is 4, and all matrix element gets done rapidly. So you freeze the population of the chain. And then you just resume, you remove the lattice, and you resume the evaporation. And the atoms are ejected one at a time, at the time you decide. It depends upon at which rhythm you compress. And they are ejected at velocities of meters per second, which is just the kinetic energy due to the very high. So you can translate them in milliseconds to a detection zone and record their states. And if you add to that millimeter wave pulses before freezing the population, you can at least detect any spin observable the same on all atoms. And you can, of course, make the correlation. It's even feasible that making transitions on the way, we could detect 1 spin observable per atom. Well, of course, these experiments, I have not told the students yet, will be very long experiments. The time cycle will be 1 experiment every 3 or 4 seconds, and you will have to average a lot of these experiments to make something that is statistically significant. So the data taking might be painful. I'm aware of that. But I will be retired when we are done.
So I suggest we let further questions for the coffee break and turn to the next speaker. Thank Jean-Michel again.